In this example here, we're continuing with the conservation of momentum, but now we're looking at an example, okay, where two ice skaters are standing together in the middle of the ice, and they push off one another. So the last example we've had is, for example, before this, we had a hockey stick that hit a hockey puck. Okay, the hockey stick came through with some velocity, hit the hockey puck. The next example we had was a soccer ball that hit another soccer ball. The other example that we did was, remember, a person jumping onto a cart, and then the person was landing in the cart, and then they were moving together. So these are the three examples we've done so far. We did a hockey puck and a hockey stick with a collision. We looked at a soccer ball colliding with another soccer ball. And we looked at a person jumping into a cart and then moving together. For the problem we're about to look at now, instead of the objects starting apart, now the objects are like starting together. So imagine if you think about two people at the center of an ice skating rink, standing still like this, facing each other. And one person pushes off. They're both going to naturally move backward because they're going to slide apart. So the question here is, this is more of a problem like an explosion problem. Okay? Again, the problems that we've done so far have not really been explosion problems. They've been more collisions. Now we're looking at the idea of an explosion here. Yes?
Do you use like this kind of physics to calculate the size, like the amount of explosion?
Absolutely. Absolutely. When you're looking at things like grenades or dynamite, momentum and energy is all used. It's mainly the energy, the potential energy inside of the, or the potential energy that the explosive has converted to kinetic energy. That's how they really determine things like how much damage it's going to do. And the momentum is the idea that all the particles are all going off in different directions. Okay? And I'm going to explain that. Remind me at the end to go back to the example of a grenade. Now, we have two ice skaters. Let's draw a little picture in the middle here. Two ice skaters are standing together and they're about to push off each other. Okay? So they push off each other and they start to separate. Now, remember from last class, the momentum initially equals the momentum at the end. That was our theory of conservation of momentum. The momentum initially is equal to the momentum at the end of the problem. Tell me, please, first of all, what is momentum? How do I calculate the momentum of any given object? What times what? Not force times velocity, that's power.
Mass times.
That's it. MV. Mass times velocity. That's momentum impulse theory. Okay? So, remember, momentum itself is mass times velocity. Are any of these two objects, or are either of these two objects moving initially? They're standing still at the center of the ice. They're not moving. So what's the initial momentum in this problem? 0. There's no need to even put a formula in here. Again, these are two objects that are standing together in the middle of the ice rink, and they are not moving. So there can't be any momentum here initially, which makes this problem a lot easier. We don't have to worry about M1, V1I, M2, V2I in the beginning. We don't have to look at that part of the equation. So what we're going to have is just to simply look at the right-hand part of the equation. M1 V1F plus M2 V2F. Again, whenever you have an example where something is stationary at first, it makes the problem a lot easier. This whole PI, initial momentum, just goes to 0. It drops off. Because again, there is no initial velocity. What are we told about the actual velocities at the end and the mass? Let's take a look. The mass of person A is 60 kilograms, and the person B mass is 40 kilograms. So we know already M1 and we know M2. We know that the velocity of person B is 7 meters per second So we know V2F. Okay, so I'm underlining on the equation the things that we know. We know the second mass. We know the second velocity after the collision, or after the explosion in this case. We know the first person's mass, but we don't know the first person's final velocity. And that's what we're trying to figure out. What is the velocity of person A after the separation? So this is what we're looking for right here.
So it would be V1F equals M2 V2F divided by M1.
Close. You're missing one thing.
Oh, minus.
Thank you, because you're going to subtract. So let's go ahead and solve, please. Solve for V1F. What's circled there? Take this whole quantity over here, move it over by subtraction. So you'll have negative M2 V2F equals M1 V1F. And then as Max said, we're going to divide by M1.
Wait.
Go ahead, Jeff.
Are we looking for A?
Yes, so I'm calling it 1, A and B. This is A and this is B.
So then why'd you... Oh, okay. Well, see, are we allowed to plug in?
Sure,
I got
absolutely.
60x plus 280 instead of...
Yes, that's fine. Equals 0 and then solve. Yeah. Either way, you're going to end up getting 280 over 60, right, Jeff? And a negative?
Negative 2.
So we got, good. Yes, negative 4.67. Why is it negative? If one person moves this way and they push off each other, which way is the other person going to move? The opposite way. So this person, let's draw a little indicating factor on here. So this person, we'll say this is person A. They end up moving away with a velocity of 7 meters per second. That's the one that we know. And that's positive. So the other person, if they push off, must move in the opposite direction. And it turns out that V1F, as Jeff said, is 4.67.
Are you on our test?
With a negative.
On our test, do you give us M1 VF?
You're given this right here. Take a look at the board.
Just that.
Yeah.
So we have to memorize.
You have to. Well, it's not memorizing. Let me explain this, guys. Again, this is not memorization. You're given on the test this formula. P equals mv. And I'm just saying the initial momentum, that would be, you put a 1 here and put a 1i. That would go over here. And then a 2 and a 2i. Then on the right-hand side, momentum F is just equal to this plus this. So you never want to memorize this formula because it's going to change. Like, see how we had a 0 here? There was no need for the other part. If you go back to the last example from last class, we had lumped the masses together because the person jumped off the cliff and landed in a cart, and then they were together afterward, the person in the cart. So we put those masses together and just gave them a VF together.
For when you're at this stage, 0 equals M1 V1F plus M2 V2F, you just, that's it. Can you just plug in the numbers and then you get 280 equals to 60 VIF, and then
280 plus 60 V2F, V1F,
then you minus the 280.
and then divide by the negative 60.
You get the same answer.
Correct. You're going to get the same thing. Yep.
Negative 280 over
Is there a test next week or some sort of assessment?
Next week?
What did you say?
No. Your next test is not until like a few days before midterm, yeah. It's about 4 or 5 days before midterm. Remind me at the end of class, if you have time, I'll talk about just stuff that you might have over break. I'm going to give you like a review packet for the midterm and stuff to work on. Okay? So, let's take a look now. I want to make sure we're clear on this. First, which person A or person B, had more mass? Person A or person B had more mass? A. But person A had a lower velocity. It's 4.67. Now, person B had less mass, and they had more velocity. More velocity.
That gives it less
It's like, if you think about it this way, if I took, remember the example I said the other day? If I took a baseball bat and hit a golf ball, how much further it goes? It's because the object has less mass, and you're applying the same amount of momentum, it can go further, or it can have more velocity. Let's look at an example of this real quick.
You're trying to do that problem now, you'd have to take in position of where the kid was too, right? Because like,
Sure,
if the kid
absolutely.
was more towards the middle, then you would
It changes completely. Yep, absolutely.
Does that,
That's fluid mechanics right there.
does that big balloon thing have to be at a certain air pressure?
Sure, and that's a similar thing. If there was too much air pressure, it wouldn't work, right? it would hit, and the big guy would probably bounce off. The fact that it was deflated a little bit caused him to be able to sink in, which changed so the internal pressure, using what's called Pascal's principle, we'll learn it this year, is that the pressure is the same throughout the inside of the container. Transfers all that momentum into the front of it, which causes that guy to launch off. All right, let's go. A pickup truck is carrying a 1,000 kilogram steel beam while cruising at a velocity of 25 meters per second. What does cruising mean?
Same speed.
Yeah, constant, same speed, good. The beam falls out of the back of the truck at a velocity of 18 meters per second. And the truck suddenly accelerates, obviously, because it has less mass now, to a velocity of 30 meters per second. Determine the mass of the truck. Okay, I'll let you write. Take a second to write, please, and then I'll discuss what I want to think about before we actually get into it.
You assume the acceleration is 5 meters per second. That's just
No, because they're different masses. So the delta V is definitely 5, but think about like PI and PF30, okay? So here's what we've got. I want to see if anybody can clearly demonstrate or tell me what's going on in this problem. What's happening? How can we think about this problem? What's the easy way to look at it? Because it might seem tough at first. Fernando, give us a starting point. Go ahead.
So, you know that the initial velocity is 25
Of what? The initial velocity of what?
of the steel beam.
Of the steel beam? So it's traveling on its own? The steel beam is floating?
On a truck, so wouldn't it be going the same speed as the truck?
Good. So together, let's say. Together, they're going 25. Everybody, again. Here's our initial part of the problem. There's the pickup truck. Here's a steel beam in the back of it. Okay, that's maybe tied down. Okay, so the steel beam is roped down. And unfortunately, the rope's going to come off. We're going to see in a minute. But together, they have a velocity of 25 meters per second. So we're going to put VI and just make it 25 instead of putting like V1I and V2I. Because again, initially, these two objects are together. Okay, it's similar to the ice skating example. The people were together in the middle, except they had no velocity. So we didn't have to worry about it. But now the truck and the steel beam are together. They're one object.
So then let's call it the beam 1. So then V1F would be 18 meters per second, and V2F would be 30 meters per second.
What is the velocity of the truck?
Okay, that's one clarification here.
Well, you will find the velocity of the truck. How do you
Yeah, you have one.
No, I mean the mass of the truck.
One clarification, the beam falls out the back of the truck.
Yeah, so it's negative.
There you go. So let's take a look at this problem now. Call the beam object 1. Call the truck object 2.
Wait, can I ask a quick question?
Yep.
If it's falling out the back, but technically isn't it kind of moving with the truck? Like it's not going back.
Sure. Yeah, sorry, I apologize. You're right.
True.
He's absolutely right. It's still positive, and I was just about to think about that. Fernando, let me clear that up because I misled you there. So the beam falls out the back of the truck, so its velocity slows down, but it's still technically moving forward. And that's the idea that, remember how if you were to really toss an object out a car window, it slows down, but it's still technically moving forward, and then it'll slow down and then it'll come to rest after a while. So that's my mistake there, sorry. Okay? Keep it as a positive there. Again, it falls out the back of the truck, but the beam is still technically moving forward. It is just slowed down now, God bless you, because it's no longer being pulled forward by the truck. Okay? So, in this problem, we have momentum before equals momentum after. Same as always. Let's go ahead and write that. This is why, Jeff, I said a minute ago, don't memorize that general equation. Because now, if you think about the momentum beforehand, the masses are together. So beforehand, we have m1 plus m2 times the velocity initially. Again, the momentum beforehand, there's only one momentum beforehand. There's not two momentums. The objects are together as one object in the beginning. So before this problem even starts, we think of this as like a lumped mass, meaning that these two masses are one object and they have one velocity together. But after the collision or after the explosion, whenever objects separate, I say explosion. Whenever they come together, I say it's a collision. Okay? So after this explosion, in a sense, we have separate entities.
Can't you divide them?
Say again?
Can you divide masses?
Well, that's what we have to figure out. We need to figure out, first of all, we have our givens. I shouldn't actually, let me just put this on the next page. Can I copy this page? Let's see.
Useful astronomical data.
Go to what are we looking for in this problem?
Index.
Mass of the truck.
The mass of the truck, which is M2. Again, we're looking for the mass of the truck. The mass of the truck is 1,000. Oh, the mass of the beam is 1,000.
Yeah, I know. So that wouldn't that mean the truck is subtracted by 1,000?
In a sense, yes. The beginning object is. Yeah, but let's fill in our blanks to make it easier. Let's write this down, people. The mass of the beam is 1,000 kilograms. That's given. And we're trying to find the mass of the truck. With all the givens up here, this is actually a very easy problem. The difficulty that people have is the following. The mass of the truck is M2. And notice, it's here, there's M2, and it's also over here. It's in two locations. The mass of the truck is right here, and it's right here. So we need to somehow lump them together so we can solve for M2. You can't solve for M2 in two spots. So in algebra, if we had a missing variable like x here and here, we would say, let's distribute the VI, combine like terms. So it might be in your benefit to plug in numbers at this point to make it easier for you. Because it's not very obvious for some people right away to know what to do.
They don't cancel out?
No, they don't, because they're not in every term. Remember, masses only cancel when they're the same mass in every term. Let's plug in numbers. You don't hear me say that often. Now it's a lot easier because we can think of M2 as x as our variable to be solved for in the equation. And it's a lot easier to look at. If you look at the previous line, a lot of people get confused and they're like, which M2 do I solve for? But now you can see, well, just distribute the 25 here. Take your 25 and distribute it.
You just said to do it algebraically. That is...
Take your 25 and distribute it.
No.
I'm going to keep solving here. Yeah, again, guys, in the notes you'll see I solve for it algebraically. I'm recommending right now that you do it just this time, plugging in numbers so you can see what's going on. Take a look here. M2 occurs in two spots. It's like X occurring in both spots. Combine like terms. Subtract 25 M2 from both sides.
7,000 equals 5 M2.
Where'd you get 7?
What?
Subtract 18,000 from both sides now. You're going to get, what did you say, Paul?
7,000 equals 7,000 equals 5 M2, and you divide by 5, and you get 1,400 kilograms.
Again, subtract 18,000 on both sides. As Paul said, divide by 5. Dividing by 5 here, what did you say we're going to get, Paul?
You get 1,400.
Any questions on this one? I know it's tricky, but the idea is this.
Wait, how did you get 14,000?
1,400. 100. Divide by 5? Here's what I want to do. I want to summarize conservation. And here's what I'm going to do. First, you can have collisions, or you can have explosions. Now, for collisions, you're going to have the following. That's our general formula for collisions, the one that we started with the other day. For objects that have some sort of explosion involved, we have this. The objects are lumped together at first, with some initial velocity together, and then after they explode, the two objects are separate from one another. So you write them as M1 V1F plus M2 V2F. Now, there's a subcategory for collisions. So let's put another equation down here at the bottom for collisions. Again, if the objects collide, they hit together, and then they separate. Again, if you want to write a little note in the margin, please write this. When the objects collide, but then separate, is when you're going to use this equation here in blue. Again, in the blue box. When the objects collide, but then they separate afterward. Now, what if they collide, but we look at, let's let the fire truck go by. Think of the example yesterday where the person jumped into the cart and then they were together afterwards. So imagine there's a skateboard on the floor and Paul decided to jump on the skateboard and hope that he stays on it. Be careful because you might obviously slide off. But imagine you just jumped, landed on the skateboard, and then you guys started moving together. Yes, so we have M1 plus M2 at the end now. So let's write this one.
That's how I broke my arm. I was playing football on the skateboard.
You told us the story last time.
That's how I cut my shin open. This is how I broke my arm.
The next. So again, before the collision, the objects are separate from one another. So if the skateboard were stationary, imagine the skateboard were completely stationary and the person just jumped off the desk. Then there wouldn't be any momentum from the skateboard. So you might have this going to 0. You don't have to draw that. You don't have to write that in. But if say one object was sitting by itself, standing still, and the other object jumped and landed on it, this is the scenario we have here, scenario 2. But if one of the objects was stationary, then the object's momentum, M2, would just be non-existent. So this right here, and if you want to write this, you can. I'm not going to write it. This would be like the person jumping off the table. This would be the skateboard standing still. This would be the two of them afterward together. It's the opposite of the explosion. Look at the equations, please. If you jump on an object and you stay together, as opposed to being together at first, and then the object's exploding, those are exact opposites of one another. So you're going to see the equations are the same, except they're switched. Okay? Beforehand, they're separate. After, they're together. Down here. But with an explosion, beforehand, they're together, but afterward, they're separate. So a grenade would fall into which category, obviously? Explosion. Because the grenade initially has a lot of pieces of mass. That's how a grenade works. Imagine somebody throws a grenade, they're at war, okay? There's a lot of little pieces to the grenade that it makes up. Once the grenade explodes, the mass of it goes in every possible direction. Comes out at you, okay? Goes into that direction. So the mass goes off in every direction. Well, initially, here's what we have to think about. The grenade initially was at rest in a sense. Imagine somebody, pulled the pin and just put the grenade on the table. Okay? It would be sitting there with no momentum initially. Does that agree? Because it's sitting still. But when it explodes, all the little shards of shrapnel have velocity. So how is that possible? To have no momentum initially, but then at the end you have all this momentum going off in every direction.
So we say it sort of has like a potential energy, like explosive potential energy.
That's one thing, yeah. It's got potential energy.
Spring.
Yes, exactly, right like that, very good. But what happens afterward? All the little pieces of shrapnel have momentum. So we have, think about this for a second, ready? Excellent, there we go. Nice. So that would be this. That would be this example right here, where it has some initial velocity, the grenade. So here's the grenade. Okay, that's the grenade. You would have some VI because you tossed it. So this would have momentum initially. So the overall result would have momentum. And that would be because that piece going forward would have more velocity than the piece going backwards, so they wouldn't cancel out anymore. Mash.
For what you just described, like when the final number is 0.
Stop talking, gentlemen.
When does that actually happen?
When you find the actual, say again?
No, like when the final number is 0, like when does that happen? Like,
If the object initially was at rest, then the object at the end technically is at rest. Remember the ice skaters? They were sitting still at first, and then we found their velocities, and one was positive and one was negative. If you multiply those by their masses, you'll get 0 for the final momentum. So as a whole, the two ice skaters have no momentum. But individually, they have momentum, but they happen to cancel each other out. Same as the grenade. Each piece of shrapnel has momentum, but the momentum from each piece ends up canceling each other out. So as a system, there's no momentum. But each individual piece does have momentum. Okay? It's the idea of a balance. The momentums are balanced by each other. Dan, Tom.
If you just had like it on the table and then you spun it, would that count as like an initial
That would be rotational velocity, which is called omega. And that's a little bit different. It would affect the problem, though. Yes, it would definitely affect the problem. All right, so, okay, where beforehand, there is no momentum of the grenade. But afterward, there's got to be some momentum from all the shrapnel, right? But isn't the shrapnel going off in every direction? So watch, ready for this? Here's the grenade. Here's one piece of shrapnel. Here's another. What happens to their momentums? They cancel out. The momentum from one piece of shrapnel cancels out the other momentum. Watch. Here's another piece of shrapnel. But don't you have another piece going off in this direction? They cancel. So the overall...
But they're not the same piece, though.
They're not. They're different pieces and they're all different masses. But if you lump them all together and look at all the little pieces of mass and all of their velocities, some being positive velocity, some being negative velocity, all those momentums will cancel out, giving you still a momentum of 0. Each individual piece of shrapnel, has momentum, but as a system, gentlemen, listen. As a system, the overall grenade has no momentum initially, and all the pieces of shrapnel summed together afterward also have no momentum.
Bad idea, yeah. I was playing Call of Duty.
I don't know what he's doing.
I think he just walked out, fought it, and came back in.
Yeah. Sorry, ladies.
He paused. If you throw a grenade and whatever explodes, and the piece explodes if the piece that explodes in the direction that you're throwing it, is that piece going to go farther than the piece that's going in the opposite direction?
Because it had some initial velocity. Then that problem would be this, Garrett. Over the weekend, you already did the first problem, so there's really only one more to do. If for some reason you did not do this, you didn't do the first one maybe, make sure you get to it this weekend. So this is what you did last night. This is what you're supposed to do this weekend. If you didn't get a chance to do this last night or 2 nights ago, make sure you get to both of them. Any questions on this right now, guys? Okay? Jeff, come on. We don't need to know about it. Example.